Yes.
Hello to everyone. Welcome to today's Middleton Group Masterclass session called Invisible Electrical Dangers, Mitigation of Electrical Hazards Caused by Earth Faults. For those who don't know us too well or haven't attended a session before, Middleton Group is an Australian-owned and operated specialist electrical engineering organisation working across the power utility, renewable energy, rail, water and heavy industrial sectors. Our organisation has been founded with the sole purpose of working collaboratively with our clients to ensure the successful and sustainable delivery of projects. We are also firm believers in knowledge sharing with the wider community, and this is why we're here today. Today's session will be presented by Scott Mitcherson, who is a principal earthing consultant with us at Middleton Group and has many years of experience. Today's session will run for approximately 30 minutes with the remaining time open for questions. Just some quick conference room housekeeping before we begin. Can I please ask everyone to keep your microphones on mute unless speaking or have an urgent question? Alternatively, place your questions in the chat and we'll be able to get to them during question time. At the end of the presentation, I'll post a short survey link which will help us bring you more interesting presentations in the future. Thanks everyone. Over to you, Scott.
Hello. Thanks, Jack. Yeah, so if everyone could go on mute, it'd be appreciated. And look, I'm honoured. I've seen some of the people that are joined to watch this presentation. I'm honoured by the quality of people that are viewing this, and really appreciate that. So, invisible dangers. So, as we all know, as electrical engineers, touch voltages, etc., you can't see them. So, today's presentation is to learn a little bit more about how we identify them and mitigate them. So, mitigation of step and touch hazards. So the messages that would be nice for you to take away today. First of all, I did do a presentation a few weeks ago on where are the dead bodies. We just do a bit of a review on that first. So we're going to look at what is a hazard. We're going to define what a hazard is, whether it's conforming or non-conforming. Have a look at how we might be able to identify the hazards and look at how we can mitigate these hazards. And we'll have some time for Q&A at the end. I think presentation goes for about 25 minutes, but see how we go. So just to recap on the last presentation, there was no confirmed deaths as far as I know from step and touch voltages. That's the bones of it, I guess. At the end of the day, there are no dead bodies. Anyone's had ventricular fibrillation, heart attack, etc., from the touch voltage has probably been just put down as a heart attack or something like that. But so yeah, the answer was there was no dead bodies. Why HV earthing? Well, standards will tell you if you look into them that they're there for safety of the people, protection of the equipment, and operational reasons, so that we have a stable grid. We don't want the voltage of the grid or the frequency of the grid to be disturbed for all the other customers. So earthing helps us manage that. We looked at hazardous voltages. They can be near the substation. Quite obviously, you expect to have dangerous voltages around substations, but it can be quite far away from the fault. It can be many hundreds of metres away. The voltages can be transferred along fences or cable sheets, etc., and appear somewhere else, and again, invisible. But we can perform some testing to measure what these hazards are, and we've also got a whole bunch of standards, of course, that we can determine what the safe voltage is determined by the standards. So that's just a bit of a brief overview. And that presentation is available on YouTube too, or if you contact Jack, he can send you a copy of that presentation. So what's a hazard? So we're looking specifically at step and touch voltages. There's lots of hazards around, but let's concentrate on the electrical ones. So really, any voltage is a hazard. There's no such thing as no hazard. So we look to any voltage that may appear on a conductive surface during an earth fault is hazardous. But what's negligible and what's which is conforming, and what might be a non-conforming hazard. we determine this by looking at what the allowable voltages are. So there's two types of standards. In the past, most standards were deterministic, and what we have now really is probabilistic standards. So on the deterministic standards, you can see one on the right-hand side there. There's an excerpt out of the mining earthing standard ASNZS 3007. And you can see that we can determine the touch voltage that's allowable in the left-hand column there by simply looking at the clearing time of the fault. If the clearing time was 0.5 a second, we know that we're allowed to have 150 volts as a touch voltage on the surface during a fault for that half a second. Deterministic, so it's not having a look at much else, not looking at whether someone's wearing electrical boots or standard footwear or standing in a wet puddle with bare feet. None of those, will the person be in that location at that time? None of those probabilistic inputs are looked at in this deterministic standard. And there's other standards that are deterministic as well, but that's just an example there of perhaps what used to be. As most people are aware now, we've moved on to probabilistic standards. And the most recently updated one, ASNZS 2067, updated in 2016. And the next screen we'll be able to talk more about that one. So with a probabilistic standard, things that I just started to mention earlier about, and you can see them on the screen here, top left, the fault frequency. How often does the fault occur on that system each year? How long is it on for before the fault is cleared? What contact scenario? This is an image, so we won't see the others, but there's 4 contact scenarios. Is it on the MEN of your house? Is it in your backyard? Is it an urban situation like a conductive pole in the street, or is it indeed remote, out, like our 500 kVs or structures out in the paddocks? Because obviously the different scenarios, there's different numbers of contacts per year and different durations per contact, as you can see in the right-hand side. There's other inputs to the left. If you look down, this we can use this software to have a look at what touch voltage is allowable. We can also select step or hand-to-hand for the current path there. We can select different footwears, make it wet. We can change the soil resistivity of the surface, which will have a bearing on the amount of current that's going to flow through you. There's also surface layers there. You can see I've managed to highlight them, whether we've got crushed rock, asphalt or a concrete slab. This will change the resistance to the voltage, obviously, and have an effect on the amount of current that will flow through your body and the risks there involved with causing ventricular fibrillation. So that sort of outlines determining the probability of coincidence and the probability of fibrillation. And on the right-hand side there, you can see a curve and see that formula that the probability of fatality is equal to the probability of coincidence times the probability of fibrillation. And it's interesting to have a look at that curve there. The steepest part there is in between half a second and a second. And if we look at our heartbeats once a second, the longer the fault duration is there while you're contacting a surface with that touch voltage on it, the more likely that voltage and that current through your heart is going to be at not a nice time for your heart. And it'll coincide with the part in the heartbeat that causes ventricular fibrillation if your heart's constricted by current flowing through it at the time. So what we aim for here and for society says, look, if 1 in 10 to the minus 6 or 1 in a million, if the risk is 1 in a million, that's acceptable. Above that, we're in an ALARP, or as low as reasonably possible, practicable, region, up to an intolerable risk. But we're always aiming in design, we're aiming for less than 1 in 10 to the minus 6. That's the software's Argon, and just once again, it helps us to calculate what the allowable voltage, so you'll see it down the bottom left there, the allowable voltage through a probabilistic method as opposed to the deterministic seen on the last slide. It's interesting. I'll just have a sip of water, sorry. Interesting to have a look at fault rates. We mentioned fault rates as one of the probabilistic inputs on the last page. We mightn't think there's too many faults around our suburb. However, when you stop to think about it, there's a zone substation supplying the power in your area. If you've got copper water pipes in your house, they'll be bonded to the neutral that goes out on the street, which is, depending on the state and the area, could well be common bonded, or CMEN as we call it, and DBZS terms that likely your taps in your house can be bonded all the way back to the zone substation. That zone substation's got half a dozen or 10 feeders going out to feed your pole subs or your street subs, pad mounts. If you have a look at the, if that was 11 or 22 kVs, common distribution voltage in a lot of our states, you see that the fault rate there could be for unshielded. Not many of these feeders are shielded in the streets. You could have a fault rate of 10, which is for the southern states with less lightning around, or 40 up in the northern states with a lot more lightning, a lot more likely for a lightning strike to cause a flashover and then a follow through of your power frequency. So I'm in New South Wales. I'm going to say we've got 20 faults per 100 k's per year. If we divide that by the 100, we've got 0.2 of a fault per year. But if we've got 10 feeders that could likely fault and therefore cause EPR at the zone substation that's bonded to your house, you could get a hazardous voltage on your house. So, in this case, it could be 2 times a year or 20 times a year, or it's more often than many people think that you may have a hazardous voltage transferred to your taps or showers. I did show this one in the last presentation, but basically it shows the zone substation. We could have people working in the sub, public outside, even at a fence many metres away from the sub. We can have people working on cables. We can even have this guy who jogged up and he's having a bit of a rest against the pole there. And if this pole is a conductive pole, it's likely bonded back to the zone substation too. So if you get this fault that they've shown on the transformer here, you'll have an EPR that's shown in this graph at the bottom. That EPR will be transferred out along the cable sheets to a conductive pole where our friend here that's having a rest may experience electric shock. And even our friend over here near the fence on the other side, similarly, this voltage is transferred out along this conductive fence. And he may experience this transfer voltage that's depicted down here in the graph. He's actually going to experience a higher voltage than these workers that are closer to the substation, as you'll notice from that graph. This is just to show the extent of how far an EPR can be transferred. So if we've got a fault at the substation here at this industry, if all the plant's bonded and we've got supplies bonded out to ship loaders and up to coal loaders, etc., a fault here can transfer hazardous voltages out many metres, many hundreds of metres. So you don't need to be next to the substation to experience a touch voltage and an electric shock. So how do we identify these hazards that can be transferred around our sites? Well, we use current injection testing. In the current injection testing, we can measure the earth potential rise, the rise at the site the voltage of the soil at the site where the fault is. And we can also, through this technique on site, simulate a fault and measure a scaled down measurement of the touch and step voltages. We'll see a little bit more about that later, but quite easily, if this is our substation under test, we have a current source, an injection source, which we normally set off frequency, potentially 56 hertz, 58 hertz, because we only want to push around 5 or 10 amps around this circuit. And we don't want the fundamental, the imbalance that's returning through the ground. We don't want that to interrupt or saturate, I guess, our measurements when we're making a measurement. So we use an off frequency. And we like to inject this simulated fault across a transmission line. That's the best way to do it. However, it's quite difficult at times to get a transmission line out of service just for this test because of grid stability. So quite often we do what we call a remote grid test. So we literally put a kilometre of line out. We find a nice area where we can put a couple of stakes in the ground and build a little grid. And we can push current in the ground a kilometre away from the zone sub. And all that current we push out has to complete the circuit. And it'll come back in through the grid and put current through the impedance. You can see there, the earth impedance, any current through that's going to generate a voltage that we can measure. Now, how we measure that is we do a fall of potential run, or sometimes called an EPR run, a potential rise run, where we might go out up to a kilometre again from the substation, and we take a reference lead that's connected to the substation, and we measure the voltage of the soil with respect to the zone substation, and we get ourselves a curve. When that curve, we go out far enough, when it flattens out, we've then sort of coming towards the measurement of what the maximum earth potential rise is for that zone substation, for that generated current. Let's look at that curve now. So in that situation, if we walked out, and this is the distance we're walking away from the substation along the bottom, and the voltage that we're measuring. So as we go further away from the substation, you'll notice that the voltage that we're measuring is getting higher and higher. And if we've got a fault level of, say, 10,000 amps, and we're pushing 10 amps around our circuit that we looked at earlier, we quite simply multiply what we've measured here by that, that factor of 1,000. So in this particular case, we're getting close to, we say, 2.5 volts. So in actual fault case of 10,000 amps would give the substation a EPR of 2.5 kV. So now we've seen that we can measure our EPR, and if you remember back to the graph of our fellows working in the substations, we can measure the voltages on the fences there. We then compare the voltages we measured, and we scaled up with the allowable voltages we calculated earlier, and we might find that we've got some voltages on some fences or transferred out away from the substation that are above the allowable. So what are we going to do about it? Well, our job as designers obviously is to mitigate those hazards, to bring them down to what we term as negligible, or and which is acceptable to society. There's two mitigation techniques. We can call them primary mitigation and secondary mitigation. Primary mitigation, the steps we take to reduce the earth potential rise. If we reduce the earth potential rise, any touch voltages that we've noticed on fences and transfers, they will be reduced in proportion to the reduction in the earth potential rise. So here's something we can do to reduce the EPR, one thing, and we affect all of the other hazards in proportion. We can bring them all down at one time. The benefit here is that when we're in design, if we're trying to design fences and model fences and this type of thing, we can design mitigation for them. But in the field, there's a lot more in the field. Third-party services, water pipelines, sewer pipelines, telecommunications, that you might not have in your model. So if we can bring the EPR down in the design, we know that we're going to reduce the hazards on site of things we haven't even modelled. So let's bring Ohm into this, Ohm's law. V equals IR, or in earthing terms, we like to talk about EPR equals fault current times the system impedance. So if we want to reduce the voltage, quite obviously we either reduce the current or reduce the impedance. Or in the case of just a separated grid on its own, we call it RG, resistance of the grid. So one classic way to reduce the current is to introduce a neutral earthing resistor in the supply feeder. If you can bring your fault current from 10k down to 1k, you've automatically reduced your EPR and touch voltages by 90%. We can reduce the grid resistance or system impedance by using a larger grid or deeper electrodes. So basically putting more copper in the ground to reduce the resistance path through to the earth, which is the return of the fault current back to the supply point. There's other ways too. If we can increase our allowable voltage above what the hazards we've measured, it's another way to achieve compliance. One of the major inputs to the allowable voltage is the clearing time, as we've seen in previous slides. So we may be able to negotiate with our protection mates, there might be some of us watching here, to see if they can grade their protection to give us a faster clearing time for the particular fault that we're addressing, and therefore increasing the allowable voltage and potentially get that above the hazards we've measured to achieve compliance. In some special cases, we can, generally we try and get the RG of the grid low. If we can get it low enough, EPR is low enough, touch voltages are low enough to comply. However, that's not always achievable. Quite often, not particularly often, but we can in special cases do what we call a halo design and actually increase the resistance of the grid purposely, which will, when you look at your fault calculations and take into consideration the resistance of the grid, rather than just zero as a bolted fault, it'll reduce your current, which reduces your voltage, which reduces your touch voltages. So there's many iterations in this calculation because it's kind of a balance between, as you reduce the current, quite often your clearing time then increases and up and down comes your touch voltage allowable again. So it's a difficult one, but it can be done, and quite often we even bury the EPR. So if you take a separated, deep insulated electrode, drive it 30 metres in the ground with only the bottom 5 metres exposed to the earth, you're effectively pushing your current deeper down into the ground, and the top part of the electrode is insulated, PVC insulated, so therefore the voltage, the current doesn't leak into the ground at the surface and cause voltages of the earth there. So it's just another specialised technique. So these are all primary mitigation techniques where if we fix the EPR or get the allowable above the touch voltages we've measured, we fix them all in one go. We do a primary mitigation. However, that's not always going to work. It might fix most of our problems, but you might find there's one or two little problem situations that aren't fixed that way. So we can do a secondary mitigation. I've got some slides after this, but basically we can pop some grading rings around our item of issue using effectively equipotential bonding to bring the soil voltage up around the item. Or we can use insulation around the item, isolation sections and fences, or create a restricted zone so that potentially rather than a public place where we might use MEN or backyard, we can make it a restricted zone where we might be able to justify using urban or even remote selections of the touch criteria. So here's an example here just of a set of 3 transformers, pole mounted, sectioned off in their own fenced areas with a man-proof fence, and a bunch of gates for access for maintenance, of course. And in this situation, it's a hypothetical, but the public could potentially be exposed to the voltages on the external fence should there be a fault at one of these transformers. You'll get an EPR, you'll get touch voltages on the fences. So in this design, to reduce the voltage between the fence and the surface, the ground that potentially Joe Public's standing on, a metre from the fence, a grading ring's been installed, which is a ring that's bare copper, 500 mil under the ground and a metre out from the fence, bonded to the earthing system. And this will bring the surface outside of the fence up in volts. If there's a earth fault there, you'll have an EPR at the transformer, and all the copper that connects to the earth grid and to the ground will increase the surface voltage there, thereby reducing the voltage from the fence to the surface that the person's standing on. Interestingly enough, down the bottom there, you'll see that grading ring's out by 1.5 metres to cater for if a gate is open and someone's touching an open gate. We've managed to increase the soil voltage up there towards EPR to reduce the voltage differential someone may be exposed to. So this is a grading ring that helps in secondary mitigation. It actually adds to the whole grid as well in this situation, and will reduce the RG to reduce the EPR as well. Second slide here just shows if we've got a HV structure, we could be talking 330 kV, 500 kV, 132. If there's a fault at that structure, again, we'll have an EPR. And that fence you can see in purple at the bottom there, if it was continuous, it would be picking up the voltage of the soil very close to that structure and transferring along its conductive length that voltage to a far off point where the soil voltage is a lot lower, and potentially a large voltage can be transferred out and create a hazard, non-complying hazard further away. So to stop that voltage being transferred out along the fence, we'll put some isolation panels in there. They're potentially made of an insulating material, perhaps timber, etc. And that stops the transfer of the soil voltage from underneath that fence section between, stops it being transferred out to the rest of the fence and causing hazards. So as time's getting on, if I have a look at that, we're nearly on the half hour, so we'll allow time for some questions. But basically, just in summary, what is a hazard? Well, all voltages are hazards, as we've seen, but we do classify them as complying and non-complying, as we've discussed. We identify them using a current injection test. We can measure the hazardous voltage using that method. We can assess the hazardous voltage against the standard, work out whether the hazard is negligible or it's non-conforming. If it is, we've got some more work to do. And that work will be to develop some mitigation to reduce the hazards to negligible and using primary or secondary mitigation methods. We should also include, for the lifetime of the asset, an earthing maintenance plan as well. And I've got a suggested topic in there. Anyone that's got a suggested topic you would like us to talk about, and I'll pop one in there, earthing test methods. I might address that in a future presentation. So that's our half hour. So I know there's a bit of squash in there, but anyhow, I'd like to open the floor for any questions or any comments on that short presentation.
Scott, there's a question there from Chris, if you can see it in the chat. He's asked if there's any downsides to using NERS. It seems like perhaps everyone should use those.
Downside in using what? Sorry, if you could just make that specific. I can't see the chat. I'm looking for it.
NERS. Or Chris, if you want to come up and ask. Scott, yourself?
Yeah, that'd be handy. Have we lost Chris?
Hello there. Yeah, it's neutral. The downside in using neutral earth resistance, it sounds like there might be a few things to trade that you might mention.
Correct, Chris. There is, yeah. If you think about it, if you're going to put a resistance between your start point and the ground, during a fault, your start point will raise in voltage, pushing current through a resistor. So that point's going to raise, and that's going to raise your line voltages as well. So you need to consider insulation levels of your phase conductors as well. Quite typically, it might mean you're adding another disc insulator to your overhead lines or something. But good question, Chris, you're right. Introducing NER. We do have other considerations to make in terms of the insulation. Thanks for your question, Chris. Any others?
I have a question, Scott. Relating to the fence isolation sections along a transmission line, for instance, they work very well in, if I say in theory, and I'll go on to say now, but if you take an urban area, for instance, around Hobart, there are a number of transmission lines running past schools and backyards and all manner of things. And suburban residents are very, very good at using their initiative. For instance,
yes, I know what you mean.
Up a piece of cyclone mesh across a wooden fence panel so they can grow their
passion fruit vines. Lovely.
Whereas, now, as I understand it, another way especially in an urban area, would be to run an aerial earth wire between the transmission towers. What's your view on that?
Well, yes, yeah, that could be part of the design. All right, just to address the first part of your question, you're right. When we're looking at some secondary mitigation like isolation panels, or there's even a case I was talking about doing a special design on it's a halo, a substation, or even when we do what we call separated designs. They're a little bit special, and the danger with them is that they can be corrupted by an individual coming along and think they're doing the right thing by stringing a bit of stainless across here to put a passion fruit vine on, or installing a LV light fitting that's got to be earthed, and it corrupts your design. So that's things we have to look at when we do these special designs. Your second part there, I would imagine these high voltage structures have already got one or two overhead earth wires running along them. However, if let's say they're 66 and they haven't got an earth wire there, putting an overhead earth wire in will be a great benefit to reduce the EPR, because now your current that's faulted from a phase to structure, it's got a few different paths. It not only wants to go into the earth grid at the bottom of the structure, it can now go along what we call an auxiliary path along the overhead earth conductor into the structures either side that can help dissipate that fault current, and the ones to the side of those and side of those effectively all the way back to the supply sub. So yes, that's and it would be a design input that you would probably use prior to using isolation panels. So it's a good question and a good point. Thanks, David, that if we can introduce auxiliary paths for the fault current, if the fault current doesn't physically go through the earth in the earth grid, it's not going to generate the EPR that generates the touch voltages. Yeah, so that's a good question and a good solution, David. Thanks for your input.
Scott, another question from Kelton. He says, apologies if you already covered it, but could you revisit the halo design you referred to for primary mitigation?
I can. I'll just pop back to that slide. So it was just sort of a note in here, but in a situation, let's talk about really high resistivity soils. Quite typically, resistivities down on your alluvial plains can be quite low and therefore easier to design low resistance grids. But in higher areas, like up in mountains, I know the Blue Mountains in behind Sydney, a lot of places in Western Australia, etc., high resistivity. So burying copper in the ground to try and get a low enough grid resistance to reduce the EPR and touch voltages below the allowable, it just becomes impossible, or the expense for drilling, digging trenches, installing copper is just not viable. So we go the other way and look to use an increase in resistance of that grid to reduce the current, fault current, which, will increase depending on the protection. I'm not a guru on protection, but depending on the protection can increase the clearing time and become your foe again. But basically with these designs, done a number of them in New South Wales, we can put, as I said earlier, a deep insulated electrode in, reduce the exposure of the electrode to the soil deep down, so that the less exposure, the higher the resistance will be from that electrode, lowers the current that does dissipate if you're buried at 30 metres into the ground. When you do your modelling and your calculations, you'll find that the EPR, the soil voltage at the surface, the further you push that insulated electrode down into the ground, you're lowering the EPR at the surface, and therefore lowering the touch voltages that you could be exposed to on conductive surfaces on the surface of the ground, if I didn't make that too complicated to listen to. So they're pretty complex designs, pretty hard to nutshell that one in 30 seconds. Happy for people to phone up and have a discussion afterwards as well. I hope that's answered the question. If it hasn't, reiterate it while I have a sip of water.
Question relating to the halo design, Scott. With that deep rod, are you talking about the top half insulated and the bottom half bare then?
Correct, yeah. The top of the electrode, indeed, the whole substation needs to be insulated from the surface. So there's special culverts for a pad mount that you can purchase. They're insulated, and some specialised devices to manage how your HV conductors come in and out of that sub, so that the design, you've got to look at safety and design nowadays. This has got to last for the lifetime of the asset, so you don't want movement, vibration, etc., to cause to corrupt the insulation at that pad mount. So the pad mount's insulated. It's a separated design, meaning your HV earthing system, which is the framework of the pad mount, and the electrode is separate to your LV MEN system. That's separated. You've got to look at what the EPR will be. Have a look at your insulation levels in between your HV and your LV, your standoff insulators for your LV earthing bar and all these sorts of things. As I say, it becomes complex. But to answer your question, yeah, the whole substation is insulated from ground, and indeed the earth electrode as it enters the ground is insulated all the way down to then the bare exposed earth electrode that's deep buried, potentially 20 metres, 30 metres in the ground. Good coordination with your utility in these cases is advised. They're a good design to solve some problems. However, they do come with being specialised and need maintaining, need checking on a periodic basis to make sure that design hasn't been corrupted. Whereas your normal common bonded designs effectively can't be corrupted. They're already bonded all, as they say. And so another bond's not going to change the bonding arrangement. This separated design, you know, an unsuspecting installation of an LV fitting from the LV side of the design onto part of the structure of the pad mount, say, automatically bonds across your separation and corrupts the design. So they've got to be managed, and utilities will accept these designs. However, think about it, you know, quite often you see the situation we use these in quite often is in subdivisions. So you get a new subdivision out the back of Sydney or back of Melbourne, and you're in rural land, and that subdivision doesn't have the benefit of an MEN to bond to help bond through your overhead earth wires, as you talked about earlier, to benefit, to join to bring the system impedance down and reduce the EPR. So if we're designing a 11 kV to 415 LV type substation in a new subdivision that's, you know, potentially rural, these designs become a solution. However, in a lot of these cases, they're not far from the MEN, and the utility expects that suburbia will surround this subdivision within the next few years. And there's the preference there to then change it back to common bonded. We can do risk calculations using that software there, if I go back to it. Excuse me while I scroll back to it, try not to go past it and have to come backwards and forwards. It's further back than I thought. But in this Argon software, you'll notice, it's the next page, that we have risk down here. So the client or the utility may even consider accepting a risk above 10 to the 1 to the minus 10, 1 times 10 to the minus 6. They consider accepting as low as reasonably practicable for a year or two, where they then know that the planning department is going to have an MEN encroach from the main MEN around this, and then it can be common bonded. So it's about managing risks at the install. You think about a subdivision, you know, it might be 20 blocks of 1 acre. Not everyone's going to build a house. Not everyone's going to have their earth stakes in. So, you know, really, you're going to start with just the substate, the pad mount sub there. So all this has got to be taken into consideration in design. So we can introduce, because there's LV lighting in the streets, introduce earthing at each one of those as part of our initial earthing system in that subdivision to manage the risks. During construction on brownfield sites with zone substations, now we're building an on-site set of ATCO huts outside, and you know the urge is to grab the LV supply from the substation and bring it out to your ATCO huts. Now you've bonded to the LV side, and you're trying to transfer any faults, any EPRs from that substation out. So construction's another area where an earthing design's got to be done for your construction site and staged with the changes in the equipment and earth grid that's being installed at the zone substation. So yeah, there's many situations where it's a staged approach, and what's happening, let's manage the risks in construction, let's manage the risks while there's only a few houses in the subdivision, let's manage the risk when the MEN has encroached around the proposed subdivision, etc. Yeah, another good question. Thanks, David. If we any other questions, I can't see the questions. Is there any other, Jack? Or
God, if you go to down the bottom where there's a chat section, if of the open that up, you'll see them coming in.
I can now see them. Thank you, Jack, for the instructions.
No worries. So Mustafa had a question earlier about CIT.
Bill Salo Barnsey, Christian, Yes. Okay, Mustafa. Hi, Mustafa. Thanks for your question. When do CIT with overhead earthwires connected to other remote ends? Is there a way to estimate the standalone resistance of the tested substation grid from the CT? Excellent question. Yes, there is. The answer is yes. What we measure also when we're doing a current injection test is what we call current distribution or current splits. So what we classically do is if we're injecting, say, 10 amps at a substation, the current we're really interested in all the currents, but the current that's going in through the grid into the ground is what's going to create the EPR. We can't put a current transformer around the whole grid and measure that. So what we do is we measure all the other currents that are going away from the substation, like the overhead earth wires that Mustafa is mentioning here. So no, we're not going to crawl to the top of the transmission tower and measure the current going in the earth, overhead earth wire there, but we do this by measuring the current in all of the high voltage structures that are going up, the structures that are holding up the incoming phase transmission lines, distribution lines. They'll be connected to these overhead earth wires at the top. So we can measure the current in with a Rogowski coil in all of the legs of every structure that goes up that's connected to the overhead earth wires. And when we measure the current and the angle, phase angle, and we vectorially sum these currents. So now we know what we're injecting and we know what's going out along transmission lines. Indeed, we look for water pipes, telcos going out of the substation. They all should be isolated, obviously, and have no current in them. Auxiliary paths also going out of the substation quite often are underground cables. The cable sheaths on your HV feeders going out, if they're bonded to pad mount substations external to the zone sub, you'll have some of your current go out through those auxiliary paths along those HV feeders as well. So we need to measure all these currents. The ones we measure, we deduct vectorially from our injection current, and now we know what's going into through the actual grid. So just reading the question again, is there a way to estimate the standalone resistance? Yeah, now that we know the current that's going through the grid and we've done our EPR or our forward potential measurements to calculate the voltage, now we're back to Ohm's law. We know the volts, we know the resistance, we know the current, now we can calculate the resistance. So yeah, during current splits, without disconnecting anything to do like a standalone measurement for resistance, we can use this method. In fact, I've used current injection testing to do just that, to measure plenty of earth stakes on wind turbine generators, rather than disconnecting everything and doing individual resistance checks on individual earthing elements. Using current injection testing, measuring all the currents, where they're going, phase angles, gives you the information you need to calculate individual resistances without actually disconnecting everything. So hope that answers your question there, Mustafa. Very good question. Thanks for asking. I think everybody's certainly will learn from that one. Kelton's got one, if we already covered it, but could you revise the halo design? I think I've done that one. Mr. Tocker. Mr. Tocker's got one. G'day, Bill. Interested in halo design and any issues with covered electrodes. I've got significant concerns with the concepts for general practitioner. I agree with you, Bill. These are specialised designs and they bring rise to a number of other issues, and they can be quite specific to the site as well. So,
Scott, I'll articulate my question better with words, I think.
If you would, Bill, thanks.
They are very advanced earthing techniques that I've seen really make a mess of designs. People forget about insulation coordination. People forget about surge arrestor operation and all sorts of things. And it just seems too common that they've made their way into people thinking it's just, oh, let's just put 20 metres of PVC covered insulation on an electrode. You know, I think most people should stay well away from those sorts of advanced techniques.
I would wholeheartedly agree with you, Bill. Wholeheartedly, good point to bring up. My intention was to put it in there for, there's other methods. There's not just those couple that I mentioned. There's more, as you know, Bill. There's plenty more mitigation methods we can use. So it was in there as an indication. There's other methods, but I'm really pleased that you've brought up the seriousness of those designs. You really do need experts to be involved with that sort of design. Agreed. Thanks, Bill.
Just as an additional comment from a utility perspective, deep bore earthing is an absolute last resort.
Yes, Glenn. Yep, agreed. And as I think I mentioned, being close contact with your utility, if you're a designer, being close contact with your utility and what they envisage for the future in that area. Good comment. Thanks. It's great to have other experts like Bill and utilities like Glenn on board to be able to make these clarifications. Thanks, guys. Kelton's got a question. Thanks, Scott. Obviously, it depends on the soil resistivity, but practicality, what depths have you seen effective? I think if that's to do with what we're just discussing and Bill and Glenn had input into, soil resistivity has an effect on all designs. I think I'll leave it there with a good input from our fellow designers and utilities there.
Just another comment too in regard to your distribution pad mounts that you suggested that people might go back and common bond up the earthing systems. It'd be nice if that happened, but it doesn't. Generally, when an ASP installed an earthing system, they'll never go back to it, and we don't have the resources as a utility to go around common bonding up earthing systems. So the initial design needs to be complete before it gets approval. And also, in addition to that, the MEM may never be established given new installation practices of non-conductive water pipe and the like. So it needs to be compliant to start with.
Oh, correct. Yeah, and that's why I sort of reiterated that you need to have compliance at every stage. And it's just in my experience, and I won't mention the utility, but closely engaged. If you're going to do anything that specialise like that, closely engage with the utility, because exactly as you say, Glenn, if there's no vision that suburbia will encroach and then go to a more accepted common bonded situation, then it's potentially that design is not acceptable.
Just the mention that you can negotiate with the utility to have a risk in the Alara region. I don't think that we'd accept that. Obviously the risk has got to be in a negligible region or as low as so far as reasonably practical. Just wanted to point that out that we wouldn't negotiate to have a higher than 1 times 10 to the -6 risk.
Yep, good. Thanks, Glenn, for clarification. Other utilities have, that's all that is, in my experience. But yeah, certainly need to be talking to them, that's for sure.
Scott, one area that I've come across commonly in my work is in private high voltage installations, where very often the ownership of the installation changes hands, can change hands after a couple of years, and alterations are made by contractors who don't have the documentation from the earlier owner. So in that respect, I think the more prudent way is to avoid the more complex solutions.
Correct. Yeah, that's it. And as Glenn said, it's a really that design, specialist designs like that, even any separated designs, they're a last resort. If you can solve the problem, solve the hazards, make the hazards acceptable with a common bonded design, that it's less likely to be corrupted in the future or neglected. That's certainly a way to go.
Thanks, Scott. There's just one more question from Deminda there that I posted. He sent me privately. See that, and then we might wrap it up there.
So is that the one, some distribution designs will have to run high voltage underground cable parallel to or crossing comms gas water lines? What are the methods to reduce EPR OFI issues from Deminda? Well, that's right. Yeah, there's quite often the HV cables will share easements with other services. So they should be considered in the design, of course. So if you have a look at other standards, designers, I know I've mentioned 2067 there. We don't just use the 2067 when you're looking at third-party appurtenances, gas pipelines, CP points, air valves on lines, etc. They've all got to be considered in your design. So there's 4835 and 3853 standards for telcos and for metal pipelines. They've got to be considered in designs as well. So yeah, address those standards at the same time in your design. I hope that answers the question, or is it a deeper question?
All right, thanks, guys. We might leave it there. Actually, Deminda's followed up there.
Sometimes require maintain 15 metre and 1 metres between HV earth and comms pits, joints in non-CMN and MN areas respectively. The urban areas are very hard to achieve. This is still integration. Yeah, I think you talked about some specific restriction zones, etc., that utilities might impose. And they're local conditions to be aware of in any design. It's not just 2067 and away you go and you solve the problems. Again, as we've been discussing with some experts in the field here and some utilities, there's more than just one standard to look at. There'll be potentially local restrictions and standards from the local utilities to adhere to at the same time, correct? So design require maintain 15 metres or 1 between HV earth and comms pits. Might be just through experience that area they've imposing that restriction for good reason. Potentially there might have been some bad designs and some circumstances where they found that imposing a restriction zone was a good way to control to ensure that earthing designs are meeting the compliance that they require.
Great. All right, thanks, guys. We might leave it there. Thanks, Scott. Another great presentation. Scott's contact details can be found at the end if you'd like to reach out to him personally, or my email's attached to the registration link, so reach out to me and I can put you in contact with Scott. So really appreciate you all attending and look forward to you joining us next time. Thanks again.
I'd like to thank Glenn, Bill and Chris for their input there too. Much appreciated.
Not a problem, anytime. Thank you.
Okay, thanks, guys.
Thanks, Scott. Jack, when's the next session, please?
So the next session is next Wednesday, next Thursday, sorry, at 12 o'clock. I'll send out an email with the schedule. It can also be found in our LinkedIn.
Thank you, and thanks, Scott. Interesting session. Good refresher for
Yeah.
many of us.
No, a lot of good questions and great input from other experts in the field. This is a great forum for not only for myself to discuss earthing issues, but to have other experts and comments from Glenn at Utilities in there is, I think it's a great forum. I invite that wholeheartedly. That's great. Okay, thanks all.